Okay, so this will be an overview of the display subsystem for my core prototype. And also, it also applies to the emulator. This will be an overview of the display subsystem for don't need to hear myself there. But or at least with a several second delay, that's distracting. It's an overview of the display subsystem for my core prototype. But it also applies to the emulator as well. Uses the same basic display type. So major submodes. There's a color cell mode, which is one of the major ones being used. So it has various cell formats with different properties, and each cell can be 128, or 256 bits. There's a flag to control this, and it can represent either character cell or graphics. There's also some bitmap modes where each pixel is encoded directly. With the color cell formats, the pixels aren't really encoded directly and have to be effectively reconstructed from other information, such as color endpoints and interpolation bits. Bitmap graphics can give higher quality, but need a lot more memory than color cell, and that's the lot more memory issue is the main reason I wasn't using bitmap graphics prior to this. And even then, bitmap graphics their usage will be limited to some extent by the available memory. A lot of this stuff is controlled via the screen mode MMIO register. So you can set some properties for how the screen behaves. So screen memory, begins at this address. The F in this case basically just means it goes in the MMIO range, or at least where the MMIO range is at now. It's previously at a different location, but I've changed it. But that was mostly to allow more address space for things like operating systems and similar. And then it's at basically how to describe this address. It's near the 640 KB mark, so this is basically the same address as what was traditionally used on the IBM PCs, and similar for their display memory, at least relative to the 1 meg mark. Was initially kind of why I chose it, but and it can be up to 128 KB, partly because at least it gets up to 128K before it crashes into the MMIO registers. Technically, because MMIO is D-word address, not byte addressed. Because of this, it could be possible to fit more than 128K in here, like say 256K or or 512K by mostly relying on misaligned access. It's up to 128K. Something, yeah, something like the 100,000 lut board in the Nexus A or chip in the Nexus A7 could handle this, but something like the RDS7 128K is quite a bit much for display memory, because there's only a finite amount of block RAM. So it can also be configured as 32K or 64K. And yeah, it's in block RAM and rather than DRAM. So, and depends on the FPGA, and that is also why there's no high resolution bitmap graphic modes. Yeah, again, because high res bitmap graphics take a lot of RAM and stuff. Redrawing the screen requires low latency and high bandwidth, which made block RAM preferable. I looked into it, and it would actually require doing a fairly fast DDR or DDR2 module to actually keep up with the bandwidth required to, just do simple things like redraw the screen. So, yeah. Well, at least on a desktop PC it wouldn't be that hard, but on an FPGA it's kind of a little more limiting, because the interface to the DDR2 RAM is only 16-bit wide and requires like all these steps to actually be able to access CAS latency and RAS latency and so on. So yeah, typically things are drawn off screen and then the resulting image is copied over. In general, in the color cell modes, this involves the use of a color cell encoder, which will take the block of pixels from the off-screen frame buffer and then re-encode it into the format being used for the display. This has to be done in real time in order to be useful, but so yeah, but I'd made it work. Worked at both 100 and at 50 megahertz without too much issue, so it's not too impractical. Interestingly enough, I was actually getting apparently slightly faster screen refreshes via the color cell encoder than using a direct bitmap mode, presumably because of the relative overhead of accessing the MMIO. So, yeah. Color cell encoding isn't free, but MMIO isn't really free either. So, and with the color cell encoder, it might only have to redraw 32K bytes per frame, whereas with MMIO, with a bitmap mode, it has to redraw pretty much the entire 128K each frame. So, yeah, screen is organized as a grid of cells starting at the top left corner. Actually, wait, I forgot something here. That's a little better. Yeah, screen is organized as a grid of cells starting at the top left corner, and Screen resolution can be affected by changing the number of rows and columns within the limit of the existing screen memory. So 40 by 25 can give 320 by 200 with 8 by 8 cells, and 80 by 50 can give 640 by 400 with 8 by 8 cells. This, of course, does change the amount of video memory required. And 100 by 37 can give 800 by 296 with 8 by 8 cells, or 800 by 592 with 8 by 16 cells. This means, more or less it can do 800 by 600 with, or more or less, with 8 by 16 cells and 128K of VRAM. So modes exceeding the available screen memory may result in the screen contents wrapping around. This would be about what would happen if you tried setting 800 by 600 with only 32 or 64K, is the actual contents of VRAM would repeat multiple times over the course of the screen redraw. That's mostly because it would just chop off the high order address bits. It wouldn't necessarily be properly aligned when it repeats either, so it'd be kind of wrapped around but kind of messed up. Screen registers. They're located within roughly the last 256 bytes of that 128K region. This takes off a little bit from that 128K, but not too much. So if the register space was bigger, it might affect things by depleting with the RAM, but in this case it's only really a few cells worth, so it's basically okay. And screen mode is mostly controlled by register 0, and low bit says whether to use 80 or 100 columns or 40 or 50 columns. You would use 80 columns for the 640 or 800 modes, and 40 for the 320 modes. Currently defaults to being cleared, so that's why it starts out in 40 column mode. I might change that. Might change its starting mode at some point, but still to be decided. Bit 1 will reduce cells to 128 bits or half of their width. For obvious reasons, you can't use two 56-bit cell formats with 128-bit cells. So that is a trade-off. Basically, this is what you'd use if you were doing doing a lot more 80 column stuff at a lot more 80 column stuff with a small amount of VRAM. So bit 2 allows using 50 rows versus 25. Similar, obvious enough. Basically just changes the size or the height of the character cells, so with 50 they're only half as tall, and so there's twice as many. Bit 3 says whether to use 800 by 600 or 640 by 400 as the base resolution. Implicitly, this also changes the number of on-screen columns. At current, the timing for 800 by 600 is a little bit oddball, but it should hopefully work. namely, rather than doing it in the traditional way of, doing 800 by 600 at the faster refresh rate. It's actually 800 by 600 with the relatively slow refresh rate, so that it has roughly similar timings to what were used at 640 by 400. It should technically work, as the monitor should be able to deal with a 50 Hertz timing. So, yeah, just it wasn't apparently a timing listed in the various charts of timings, but stuff says it should work. Screen mode. So 0 and 8 are color cell. 0 uses primarily YUV endpoints, and 8 uses primarily RGB endpoints. Similarly, in the bitmap modes, you can select between YUV and RGB as the primary format. The color cell module actually does have built-in conversion logic, so it can basically deal with both in the display hardware, and there are technical reasons for why one might want one or the other. So mode 2 and 10 are 4-bit per pixel RGBI modes, so 16 color. These can go up to, or this can basically go up to 640 by 400. Can't do 480 because not enough screen RAM, and similarly can't do 800 by 600 at 16 color either because not enough screen RAM. At least with 128K. Yeah. At 64. Yeah, at 64K also can't do 16-bit per pixel bitmap at 320 by 200 either, because that takes up a full 128K to do. But you can do it with 8-bit index color or palette graphics. So, screen registers 1 through 7 are reserved for now. Haven't used them yet. So, all the VGA timings are hard-coded in the hardware for now. So, just uses a flag that says whether you want 800 by 600 or 640 by 400, and it just sort of sets the timings, but they're hard-coded. 8 is a frame number. Again, this is used by software, but isn't really used much for by the actual hardware. So it's mostly an emulator feature. Basically, it partly is used to tell the emulator how many frames have been drawn, and thus frame rate, and also partly is related to the screen redraw process in the emulator, but not really useful for hardware. See-through effort used for writing into the font RAM. So basically, it selects which are the 4 words within each 64-bit font RAM slot, or font RAM index, and high order bits store the index, basically which character cell we want to write to. And yeah, and for each of these, the low bits are written into the low word for the value being stored. This scheme was mostly because there wasn't a huge amount of MMIO space left for registers and stuff, and I didn't really want to deal with putting it somewhere else, so yeah, just sort of shoved it into a few MMIO registers. Kind of a hack, but not going to be, at least presumably not going to be doing high-speed redraws of the font SRAM or rapidly changing out the palette, but yeah. Even as such, it shouldn't be that slow because those spaces are fairly small. Cells have major modes and submodes given by the high 2 bits of the first two D words. It's basically the main scheme used for doing it. So the first number would be for the first D word, and the second number, which doesn't apply to these cells, would be used for the high 2 bits of the second D word. So the top two tags are used as 0 and 1s for text cells and for base graphics. These are not very good and are mostly historical at this point. So yeah, these were used initially mostly because I was previously using smaller cells, namely 32 and later 64-bit. Ended up eventually expanding it to 128 and 256-bit so that I could have graphic modes that weren't horrible. So that's basically where that came from. So mode 0 and 1, they're laid out as character cells. Mostly that's what 0 is mostly used for, is text mode, and 1 is mostly unused at this point. So basically high 2 bits are a tag, and a color mode. This can, well, select things other than RGB222, but that's kind of what I'm using as the default for now. There's also a mode which, has larger colors, but at the expense of attribute flags. Also not really used much because, at this point I don't really need like high color depth like letters, and 6-bit basically works. That's more than, the 16 colors you get in most text modes, so you could, conceivably actually do semi-passable graphics just with text cells. So there's attribute flags and a font and character glyph. So basically useful things. This is, granted, about twice the size of a character cell in something like Vga, but it's not too horrible. though it's still padded out quite a bit because of the way the screen memory is actually laid out. But yeah. So text cells, they have basically ASCII and the code page 437 characters for their basic font. Font 1 is mostly graphical symbols, so partition patterns similar to those in the BC7 texture compression format. These are useful for trying to draw graphics via text cells, which was originally how I was doing this, but not quite as useful for, text. And there was a bunch of pesky style symbols as well, which are mostly useful for pseudo-graphical user interfaces while still operating within the limits of a text mode. So pesky was basically the character set used largely by Commodore. Mine isn't exactly the same as pesky, but it's sort of similar styled and stuff. So fonts 2 and 3 basically function as a user font space, so it can have 512 glyphs, each 8 by 8, with the last 64 glyphs also potentially being usable as a color palette. So yeah, each of the last glyphs, they each contain 4 16-bit color indices, or colors, whatever. So they can also be used as fonts as well, but the use cases kind of would be mutually exclusive to some extent. So attributes, so there's blinking text. Blinking could be set to either alternate between 2 different colors or character values, or to basically blink by reversing the colors. So basically during one part of the blink cycle it would have the 2 colors as normal, and then the other part would just sort of reverse the foreground and background color to make a alternating blinking pattern. But the normal blinking is, fast or slow, or not blinking, which is more common than either kind. So there's overline, underline, and strikethrough, which should be reasonably obvious what they do. Basically just drawing lines over, under, or through the middle of the character cell. These are done via bitwiddly on the character cell bits, so nothing too drastic there. So mode 3.3, this is one of the main used color cell modes. This is basically the one that I was generally using for Doom and Quake and similar. So the first 4 D words function as a pair of basically 15-bit color endpoints. These can be either YUV format or an RGB format, depending mostly on the screen mode register, as noted before. So each contains a pair of colors, and the high 2 bits are tag bits, or must be 0 for the other 2 words. Yeah, so the high 4 words are basically just used for endpoint selection bits. So 2 bits per pixel interpolating between the endpoints. So basically, so this selects B or the background, or yeah, 0, 0 selects B or the background, 1, 1 selects A or the foreground, and the other 2 sort of select between 2 interpolated values for these endpoints. And each D word in this case functions as a 4x4 subblock. Yeah. So, yeah. Oh yeah, each pair of endpoints basically has a corresponding subblock, or a corresponding 4x4 pixel subblock. And in terms of how it works, it's conceptually similar to the DXT or BCN texture compression. So, yeah. Actually, yeah, you can make DXT compression go reasonably fast as well, but even if some of the tools that did that were kind of rather inefficient and slow, but you know, it's actually plenty doable and much faster than real-time speeds. So, yeah, and still real-time even on comparably slow hardware like 50 megahertz or similar. So yeah. So 3.1, basically it's the same cell layout as 3.3, but just using 4x8 pixel blocks rather than 4x4. So yeah, the selectors, instead of doing interpolation, they function as a pair of 1-bit selectors, thus allowing doubling the vertical resolution. So one applies to even scan lines, the other to odd scan lines. So straightforward enough. The reason they're the same basic layout it's used is, well, that makes the Verilog simpler, because you know, most of the work being done for unpacking one block format can be used for unpacking other related block formats, which have a recurring pattern with this. So that favors certain things, like, you know, always having the tag bits and the color endpoints and all that stuff in roughly the same spot or same places, and also using the same basic endpoint formats. Bitmap mode. So there's a bitmap mode which does 4x4 pixels per block at 16 bits per pixel. So this can basically, if you set it to 80 by 50, you can do 320 by 200. So that's how this works. Each cell holds 4x4 pixels, and the pixels are in raster order starting from the least significant bit. Yeah, that was mostly to allow easy copying from a linear frame buffer. As opposed to raster from the high order bit, where you'd basically have to reverse all the pixels when copying, which would be less efficient. So the pixels are, as controlled by the mode, are in either YUV or RGB formats. where it's YVU because U and V are flipped from their normal ordering. This is again mostly because, you know, if you have your V or your U component or your blue component in the lowest significant bit, you can just sort of shift right by one and discard that bit, which makes it easier. Not quite the same as RGB 5.5 or 5.6.5 versus 5.5.5, which is kind of annoying, but works. So, yeah, the packing. Yeah, in this format you have your Y and your high order bits, and your V and U and your lower order bits. For some tasks, like for some tasks like color selection and interpolation, you can actually get by surprisingly passable by just ignoring what the bit or what the actual bit components actually are, just sort of directly selecting or interpolating the value as if it were a single linear luma value. You can also sort of do it with RGB, but the results are, well, slightly less pretty in that case, but it still sort of works. Slight artifacting can result by directly interpolating the packed values without, like, you know, avoiding bits carrying over or similar, but sort of passable. So yeah. Setting half-width cells. Basically, yeah, you set the half-width cells, while in this mode it just instead uses an 8-bit per pixel index color mode. So 256 colors, sort of like what you would traditionally have with BGA, just in an oddball, not quite raster ordering. Screen mode similarly, in this case, selects whether the palette colors are YUV or RGB based. And bitmap mode. And there's also an 8x8 mode with 4 bits per pixel. This also reuses the same basic layout as the 4x4 mode, but further divides each what would be a 16-bit pixel into now 4 pixels as a 2x2 sub-block. They're also in raster order, so no surprise there. And each holds an RGBI value, so IRGB, and it's basically the same RGBI as you would find in the 4-bit VGA modes. So that makes it easier, but, you know, with the difference that they're, you know, packed in a block rather than, you know, 4 parallel planes like in VGA. But actually packing them into blocks should possibly, well, despite the annoying ordering, still be a little bit less annoying than the dealing with the 4 planes in VGA. But yeah, and into that. Probably won't go on quite as long today. There's not quite as much to talk about, or not as much to talk about with this, so yeah. I do have Doom, which should be set to use the bitmap modes. So this is Doom with more or less bitmap graphics. These bitmap graphics are a little bit higher quality than the color cell. So it is now possible to see more detail from the various stuff without so much artifacting. So yeah, one possibility. If I can find the right file, I can fiddle with it. Here's where it sets the mode. So what can I do? Well, one thing I can do is disable setting the register, which will basically cause it to use color cell. This will cause something different to happen, presumably. Yeah. Not quite what I was going for. Kind of. Probably still want it to have the same overall screen cell layout, just in color cell mode. So changed it again. So it can almost see stuff, but it's basically kind of garbage because, this is, not the right mode. Trying to interpret the bitmap graphics as color cell. You can also go the other way with that, so question is, what if? What if we feed the color cell data into bitmap mode, but okay, we'll have to do it a little different than that, otherwise we'll just get a mess. So 1, 0 there. now it's, yeah, 40, should be a 40 by 25 bitmap mode, or roughly 160 by 100 bitmap, but trying to display the color cells as bitmaps. Yeah, that's unpleasant. Yeah, enough of that. Just put these back to how they were. Now back to good old color cell mode, which should work. So yeah. As can be noted, this is in color cell mode rather than bitmap mode, despite usefully enough, the volume actually works in this as well. So yeah. But yeah. Despite the obvious enough limitations to the color cell, namely that it's only using 32K in this mode rather than the full 128K, and it's, you know, just sort of really crudely either selecting the brightest or darkest pixel and, you know, just interpolating them all as a single unit and all this stuff. It's surprisingly passable in terms of overall image quality. If you are doing like batch texture compression or something, these shortcuts wouldn't really fly because there'd be, you know, probably an unacceptable level of overall artifacting, but it actually works. Similarly, but it does turn out a little better in the YUV mode than it does in RGB, because in YUV mode the Luma component tends to dominate over everything, whereas in RGB mode, well, if you try doing similar, you would just end up with the red component dominating the pixel, and having the pixel values be dominated by Luma is a little bit better looking than having them being dominated by the red component. But if you are going to go that route, you'd probably at least want them to be dominated by the green component, because the green component has stronger correlation with the overall Luma than red does. But this sort of green, red, blue ordering would be a little bit weird, but would technically work. So as noted, interestingly, the color cell mode seems to give a slightly higher frame rate than the full bitmap mode, implying, yeah, sort of implying that the cost of encoding the color cells is actually less than that of transferring a full 128K via MMIO. Is possibly a little unexpected, but not too, probably not too absurd. But yeah, it was just sort of an interesting thing observing that one. Though, as noted, the 120 or the full bitmap mode does have the advantage of higher image quality, because fewer artifacts versus the color cell. But again, this color cell mode is, you know, reasonably passable. And it still looks a lot better than, like, you know, what one would get if they were trying to downsample Doom to 16 color or something. Actually, wait, I can do something here. I have to restart Doom so I can get a consistent image. So, copied a screenshot into clipboard. Now I just need to got what the crop to selection tool was for a moment there. That's what was going on there. So color cell reference. As noted, this is compiling Doom with BGBCC rather than with, like, you know, a more standard compiler, but so now I've got that to clipboard. Now we can have a direct side-by-side comparison of well, the color cell mode and the bitmap mode, which is slightly green tinted or slightly more green tinted in this case, but such are the things one might notice with side by side. But so differences in the numbers, because actual bitmap graphics rather than color cells and color cell artifacts. Oh yeah, but but given the significant abuse the image is taking for encoding into the color cell format, it still actually fares surprisingly well, all things considered. Oh. Yeah, you wouldn't necessarily expect the difference between these images is one was only using a quarter as much video RAM, so well, maybe one might suspect it with this stuff going on, but yeah. Can't remember offhand if there's a quick and easy way to convert this to 16 color apart from resaving it, but I remember there being some convenient way to get into 4-bit graphics, but at least short of loading it up in GIMP or something, but yeah. Guess maybe they don't have a feature for that because they're rightly assuming, or probably rightly assuming at this point, that hardly anyone is going to you know, find the right spot to figure out where I saved it. Okay. Yeah, that's basically just graphical scratch pad zone there. Some of it's basically just images I gathered, and some amount is, you know, past artwork. Not useful. Not quite, but the question is, will GIMP have an option to allow me to get 16 color mode? And just remembered that I think there's a program I'm forgetting. Yes, Paint. Question is, does Paint still support 16 color mode? Yes, it does. Do I want to continue? Yes, this is actually the whole point of why I bothered launching Paint. Yes, that looks decidedly awful. But I guess the point of this little exercise was, well, this would be what your option would be for 320 by 232K without some sort of color cell magic. And what I have going on here does look substantially better than something like this. So yeah. But as noted, there is the whole thing of bit twiddly magic needing to be done in the both the encoder and decoder side to make this work, and some amount of compromises as well. And as noted, this is what the emulator is producing rather than, or what the emulator's logic is producing rather than what the actual Verilog version would produce. But yeah. Offhand, I don't have any good examples of the Verilog output because, well, yeah, it takes an extremely long time to try to start up Doom with that, and it still doesn't quite get this far in the simulation. Still need to debug some things, but yeah. But gradually making progress, I guess. And surprisingly annoying to find a program that supported 16 color output on short notice. But yeah. As can be noted, my code density has gotten a bit worse in the case of Doom here, but that's because of some recent tweaks for trying to make it faster at the expense of code density. While I'm often screwing around with stuff land. What if I try to, well, set Doom to use 16 color mode? But you know, something. Despite the whole thing in this case of it being you know, kind of completely the wrong mode and trying to, you know, display the 16-bit graphics as 16, or as, yeah, display the 320 by 200 16-bit image as 640 by 400 16 color. Actually, it's actually surprisingly passable in the sense of I can still see what's going on. Colors are completely weird, but you know, that's not really unexpected. I guess in this case, each different possible color will in turn be transformed into a pattern of pixels, which I guess it could maybe actually sort of work if you know, had a non-random transformation, like a sort of poor man's dithering. But yeah. Yeah, you'd probably want to have it dithered in a way where the colors produced are at least sort of in the same general area of what they're supposed to be. More surprisingly about this is that it also seems like it vaguely preserves Luma, even despite being pretty much arbitrary. But yeah, probably enough of this, because that's still not particularly pleasant to look at. So. Yeah, lots of different possibilities exist with that. No logic currently in place for doing Doom as index color, but could maybe do that if needed, which would be, ironically enough, going full circle and putting Doom back into the mode of which it's theoretically supposed to be. Figuring I'll launch up Doom too, since I haven't messed with that in a while. funny is, yeah, Doom is at least a bit closer to, for the demos, matching the, what the engine expects in this case, but it's still not quite right. Turn the music all the way down because it's distracting, but yeah. Doom 2, at least, yeah, it also looks a little better with, like, you know, actual bitmap graphics. Oh, as noted, it is rendering in a YUV bitmap mode rather than like something like RGB 555, but or RGB 565, but yeah. Either, but yeah. Well, considering it's upsampling from 256 color, the choice between RGB and YUV in this case wouldn't make too huge of a difference. So, second level of Doom 2. Nothing too notable there. Funny is when I converted the this version of Doom over to using, you know, the 16-bit YUV rather than, you know, 256 color, the logic for like the fuzzy demon and similar had to be, you know, completely redesigned, but surprisingly still works. Or surprisingly still works about the same as it did originally. Basically, the way some of the effects were done were quite tied to the specifics of how the color palette worked, so had to redesign the logic in some of these cases, but yeah. And Doom has crashed. I've seen this bug before, but don't think I've quite figured out what's causing this particular crash. But I've just noticed if I in that level in that particular way, it seems to crash. just remembered that I was going to do something, but I almost forgot about it. This will work. So the question is, what if I change now what if I change the console startup to use a different mode? Copy this over because it's basically the same logic. So probably will want to change some of this other stuff to match the actual width of the console. It can be noted that in most setups now I do actually have the necessary amount of VRAM required to support 80 by 25 consoles, which is admittedly probably an improvement over 40 by 25 consoles. Probably don't actually need to rebuild that. I'll need to modify Doom to the correct mode. And yes, I have the necessary had the necessary logic or necessary folder in place. So yeah. Now, want to do like the other one. Modern Windows makes me wish, like, or miss older Windows having this useful feature of being able to mouse scroll wheel to get through that quicker. Or like, now you have to wait because being able to scroll wheel there is too fast and too convenient. So just make all that stuff 80 by 25. That doesn't need to change. Rebuilding Doom does need to change. And see how it goes. Kinda still looks like crap, but or the text does, but it is probably acceptable. You know. Yeah, the main alternative would require, you know, doing like VGA and using a 14 or 16 pixel font in 80 by 25 mode. Yeah, that is of course, like, you know, less convenient. For some of my other uses where I was using BJX2 as a VM, I did go and change out to a higher resolution font to make it look nicer, and kind of redesign some of the font glyphs as well to look better, but those changes haven't been, you know, put back in the emulator version, and also wouldn't really map up that well to the actual hardware anyways, which is kind of mostly stuck with the use of 8 pixel fonts, unless I go and design it a bit further, or redesign it a bit further and support 8 by 16 fonts, which I could actually do, but either way. Yeah, this here is back to using color cells. See how well Quake fares. basically, since I changed the console mode, I'm going to have to change change what Quake is expecting, or have Quake change the mode as well, so it's back to the correct mode. Haven't looked at this logic recently, so old stuff related to the original like Super H version, which differed in that it differed mostly in that it was trying to emulate the Dreamcast display hardware, which is a bit different than what I'm currently using. But what I want to do here just copy this over directly, because this logic, that's close enough. The other part here is probably sufficient to leave it, because I might later go and copy over the logic to use a bitmap display for Quake as well. But yeah. Now I'll see. Is it good now? Yeah, that's a little more how it's supposed to look. Quake is, of course, still rather laggy at these speeds, but yeah. Quake probably isn't going to be particularly usable on my FPGA prototypes, because this is still faster than it's going to be on the FPGA prototype. In the FPGA prototype, it's actually stuck running at about 50 megahertz, which is actually about half the speed, which has not particularly pretty effects on the frame rate. Can't tell if I'm doing too much worse than the original PCs here, but yeah. How long have I been running? Yeah, almost 2 hours. reacquainting myself with Quake's logic for screen redrawing. Color cell stuff, more color cell. Part should match up more or less. That part's no longer valid because I changed how that part works, and so it's done instead this way. Just copying, pasting over this logic really quick, which should hopefully work. I'll see if it doesn't blow up. Doesn't match up, but I can probably just comment it out because this logic doesn't actually apply to bitmap mode anyway, or that those variables don't apply to bitmap mode anyway, because they were related to the color cell stuff. So try again and see if it works. Now Quake should be in bitmap graphics. is in bitmap mode as opposed to color cell. Now I'll make it go some semblance of actually fast. So yeah. Since last time I did fix the console scrolling issue, so yeah. Just sort of turned up the emulator speed there because yeah, don't necessarily need. Oh. There is a little detail of Quake I momentarily forgot, which is that it automatically forgets a cheat code in level change, unlike Doom. Whenever you change levels, you have to reload your cheat codes and stuff. Otherwise, it'll forget. Also, the sky is solid. At least sometimes. Other times the projectiles just disappear. But right now they seem mostly intent on exploding. crashes again this time. It did not. Crashes are annoyingly intermittent sometimes, but yeah. Sometimes it's not always obvious whether it's a bug in the compiler or a bug I'd introduced in the code somewhere or something. Thinking if there's something else I can do here. For a long time, it has only been including pack-o-pack, which makes it shareware. Pretty sure I have the other pack file still there. No. Kind of pointless, but easy enough to fix. That change, be able to go to different episodes. was getting kind of dull always going to episode 1, but yeah. Enemy I haven't seen recently, because he is not an episode 1 enemy. Guys were sort of in the way, but yeah, this is possibly getting off track from talking about display subsystem, but someone there got stuck in a door. May or may not be a bug. Who knows? There's always a certain amount of, you know, always a certain amount of faith with that. Namely, one can never know for certain what subtle changes in behavior are, you know, actually the case or a result of subtle compiler bugs. Or similar. Or like other subtle changes like floating point precision or like due to the lack of denormals, because in here I don't bother emulating denormal values for floating point stuff. In fact, the whole floating point thing is mostly being done with integer math on this, so yeah. But we don't really need to care too much because, well, modern CPUs are way faster than old style ones. is noted, because I can just, you know, casually, and now it crashes. But yeah. What has it done? It has triggered this breakpoint again. Because presumably it doesn't like the values I'm getting out of cosine or something. Yeah. Challenge sometimes is remembering which file some of these functions are in sometimes, but yeah. No, what breakpoint means probably one of these values is outside of range. Which one was it? Looks like R4 is my constant, R5 is my reference. So this value is very slightly below, just ever so slightly below 1.0. But it is of course enough for this logic to care about that. Could of course go and try to debug that, try to figure out, okay, why are my sine and cosine giving values that are slightly outside the specified range, but I can also do this. Because, you know, could debug it, could just not bother for right now. You know, make Quake work, even if its math is very slightly off. While I'm at it, see how fast I can go. How fast can I go right now? Well, manages 700 megahertz. Will it handle 900? Okay, so it's like, yeah, it's managed 800. Yeah, so it, trying to run it at 900 as a result. It didn't going at 800 and slightly slower than real time. Not too surprising. There is a limit to how fast I can emulate this thing, but so I've basically gone and turned it up to speeds roughly comparable to something like a Raspberry Pi. As for whether or not I'm getting comparable performance to performance per clock to a Raspberry Pi, I don't actually know. Depends a lot on compiler optimizations, probably. I'd expect that my instruction set should probably be able to perform slightly better per clock than an ARM chip, but not really sure. As despite not lacking some capabilities an ARM chip has, it has some other things it can do that the ARM chip can't. Like, for example, So random occurrence there of playing Quake slightly closer to how it's meant to be played. Oh. But that was, of course, actually due to a screw up, but... So, Open Sesame Launcher. So yeah, Quake has kind of annoying zombies. And that you have to rocket launch them, or else they come back. Not necessarily responsible for Quake's anti-religious imagery, but yeah, that is one of those things. I suspect that was one of those things which was just sort of a thing back in the 90s or something, but yeah. At this point I can't remember where we're supposed to get the gold key out here, but oh. Never mind, it appears I've got it somehow. basically just getting distracted at that point, but yeah. So it has maintained 800 megahertz and keeping the timer interrupt at its expected frequency. So, maintaining real time at 600 MIVs. Granted, if a person were trying to make an emulator for a console intended for serious game playing and stuff, they'd probably need to make the performance a little better than this, but for, you know, basic hardware simulation, it's pretty much sufficient. Or hardware emulation. And, you know, the emulator is still way faster than the actual FPGA version would do. Interestingly enough, even on my phone, it's still roughly comparable to what the FPGA or PGA version should be theoretically capable of. So yeah, emulator on phone still somehow manages to run circles around DOSBox and similar, which deliver performance that's kind of not terribly satisfactory. Like making Doom look like a slideshow. Kind of similar to what happens on the Raspberry Pi as well. My phone is a little faster than a Raspberry Pi, but doesn't seem to be enough to make a huge difference. Well, despite differences in clock speed and operating mode, because 64-bit ARM versus 32-bit ARM, and you know, my phone runs at an epic 2 gigahertz, so it's a bit faster, but interestingly enough, still the same kind of ARM core that's used on the Pi 3, so yeah. So basically like a slightly overclocked Pi 3. Still fast enough to run my emulated CPU core at well, fast enough to do 50 megahertz. It's a little bit more of a stretch trying to get 100 megahertz out of it, but yeah. But it does 50. Streaming, so I don't necessarily need to look at my email right now. But yeah, just getting distracted. I think I'll call it good for now.